And then finally, with respect to Hill's criteria that were established in the 1960s, he was tremendously against the use of statistical testing as a means by which causality can be concluded. He explicitly rejected the usefulness of statistical significance testing for causal inference. He specifically said that no formal test of significance can answer those questions, and that such tests can and should remind us of the effects that the play of chance can create, and they will instruct us in the likely magnitude of those effects. Beyond that, they contribute nothing to the proof of our hypothesis. And far too often we deduce no difference from no significant difference. And so his point was well taken at the time, that the presence of a statistically significant finding alone, in the absence of all those criteria being met or partially met, is not in itself proof of causality. Now, this table comes from the Rothman paper that summarizes the key problems with those 9 criteria that were specified by Hill. And again, I would say that the temporality criterion has to be met. It's very difficult to find problems with that criterion. Now, Rothman will say that, specific to that it may be difficult to establish a temporal sequence between cause and effect. But again, fundamentally, in order to prove causation, you have to be able to show that temporality. The other arguments make sense and should be taken into consideration when viewing these different criteria, as well as the counter arguments for them. So now I'm going to walk through the scenario of smoking and lung cancer and walking through some of those key criteria to conclude that there is causation occurring. This particular table here is to illustrate the strength of association criterion of Bradford-Hill's, illustrating that with the presence of smoking, the relative risk, the incidence per 100,000 is 122.6, but in the absence of smoking, the risk of lung cancer is only 11.3%. That gives us a relative risk of 10.8%. and a population attributable risk of 90%. Here, this numerical example of a strong strength or a large measure of association between that factor smoking and the outcome cancer. That could be expanded further, and that's shown here, where you have a different risk factor that can also be associated with the outcome of lung cancer, in this case asbestos. And again, it's to show the strength of association between not only asbestos and smoking, but asbestos and non-smoking. So while asbestos is a known risk factor for lung cancer, the strength of the association, at least in these data, is less than that for the smoking risk factor. And the population attributable risk is small. It's only 1%. Compared to 90 for smokers. This is looking at the combination of the smoking risk factor as well as asbestos on the overall relative risk. And it's illustrating the combination of the two, which is not additive, but rather multiplicative. And to illustrate a couple of things, one being that these two risk factors collectively add to an enhanced risk of lung cancer. And it also plays into that idea of the multifactorial causal mechanism at play. The next criterion that I'll walk you through with an example is for the consistency. And specific again to smoking and lung cancer, virtually all studies conducted show a positive relationship between smoking and lung cancer. And that includes everything from prospective cohort studies to anecdotal stories or case reports. And we now have several years of data on this, but imagine back in the day when the Public Health Service was investigating this and essentially charging tobacco industry with killing people with smoking. There wasn't as much evidence then, but there's much, much more now to suggest that there's tremendous consistency for that association. Now I'm going to walk through an example of linearity. This figure shows that with the increased number of cigarettes smoked per day on the x-axis, that there is a linear increase in the standardized death rate per 100,000 men per year. This also illustrates some consistency because it's showing the data in different groups. Now, this shows linearity in an opposite relationship by numbers of years stopped smoking and the annual death rate. Now, you're noticing here we don't have exact linearity, but more of a exponential distribution. But again, there is a relationship going on here between smoking years stopped smoking and death. Temporality. This, of course, as I've said throughout this set of videos, is an absolute necessary criterion. Does risk factor precede the disease? Does smoking precede cancer in majority of those studies, other than perhaps some of the cross-sectional studies? There is evidence that the smoking preceded the cancer. And then that can be explored even further with respect to the age of the initiation of smoking and the point in which the disease occurs, which has been demonstrated through a variety of cohort studies. Coherence criterion. Does it make sense biologically that smoking can cause lung cancer? Carcinogens have been identified in the smoke, and then that's been replicated in animal models. So there has been proof of coherence, or that the coherence has been established for this particular outcome or factor-outcome relationship. Now I'm going to walk through a second example, and this has to do with the causal role of the H. pylori infection and duodenal ulcers. And it has only been in the last several years that we've understood this causal role. And this particular example puts together all those the key criterion that led us to conclude that there is this causal association between this infection and this type of cancer or ulcer. So this first one would be the temporality criterion. And here it's been proven that the H. pylori infection is clearly linked to chronic gastritis. It's preceding the gastritis. Specifically, around 11% of chronic gastritis patients go on to have these duodenal ulcers over a 10-year period. So relationship between the gastritis and the ulcer, and that the H. pylori causes or is linked to, I should say, the chronic gastritis. As far as the strength of association, it's found in over 90% of patients who have the duodenal ulcer that they also have had this H. pylori infection. So it's a large measure of association. Dose response has been demonstrated with respect to looking at the density of the H. pylori pathogen in gastric mucosa and showing that that's higher among people with the duodenal ulcers than patients without. There have been multiple studies conducted to show this association, and that met the replicability criterion. As far as the biological plausibility, there has been studies to show that the H. pylori binds to sites on the antral cells of the stomach, and can follow these cells into the duodenum, and also that H. pylori is a mediator of inflammation. As far as cessation of exposure, eradication of H. pylori leads to healing of the ulcers at the same rate as histamine receptor antagonists, but that long-term ulcer recurrence rates were 0 after the H. pylori was eradicated, but not necessarily 0 after the cessation of the histamine receptor antagonists. There's quite a lot of data on the specificity, and that among patients with duodenal ulcer, the prevalence of H. pylori is close to 100%. And there's been evidence of consistency, such that the pylori infection and duodenal ulcer has been shown in both men and women. And it has also been shown in different populations. And then as far as an effort to try to find another explanation for this relationship, there are data that suggest smoking is a risk factor for H. pylori infected patients, but it's not a risk factor in patients for whom the H. pylori has been eradicated. So in that instance, the risk factor of smoking may be a additive factor, but the removal of that factor doesn't stop the presence of the duodenal ulcer. So it doesn't rule out the H. pylori relationship with the duodenal ulcer. And then finally, I want to just close by saying that there are other models specific to causation, and these are discussed in the Rothman textbook. It's a recommended book for this course. Specifically, there is what's called the counterfactual model. This is a much more complicated and advanced model used in epidemiology, but it basically has this idea of these two states. One state where the factor of the exposure does not occur, and another state where it does occur, and all other conditions of the experiment are basically held the same. And the measure of the effect essentially is the difference in those two states. But again, this is a more advanced idea with respect to causation, not a topic we discuss in this course, but is one that you could go on to study more if you took follow-on courses to this one.